Okay, so this is joint work with people in Sorbonne Université in a laboratoire d'informatique de Paris. And it is actually quite off-topic compared to what I'm doing usually, which is continuous variable quantum computing. And it stemmed out from a discussion with a French cryptographer, Antoine Joux, about swap test, basically. So, can you hear me? Is that, yeah. So I'll give you a bit of context before starting. So what are programmable quantum devices? So you can think of them in two different ways. If you have a classical program or a quantum program, the classical program, for example, would be could be a classical control in an experiment, for example. And the programmed, if you have a quantum program, you can think of the following settings. So this is from an article of Nielsen Chang a bit more than 20 years ago, where you want to actually encode a unitary that you want to apply on an input state D. And this unitary is encoded in program states here. And basically you want to have a circuit which is universal in the sense that it won't depend on the input and the program, and it will always encode the unitary on the input states here. And you have some garbage states as well. And so in this paper, they actually showed that a no-go theorem for that. Basically, you cannot do deterministic, programmable, universal quantum computing. And they actually gave a relaxation where they introduced a probabilistic one that has, in general, exponentially low probability of success. So what we're doing now is looking at another type of relaxation, where we're interested in mimicking projective measurement. And so I call those universal projective measurement because it is kind of the same setting where you have some input state phi here and a bunch of program states. Let's say it's the same copies of the same state psi, and a circuit C which is independent of the states. And you want the circuit to actually output a classical data in a way that mimics the statistic of a projective measurement, whatever the input is, right? So with that, I can give you the outline of my talk. So I'll first get a brief detour through the realm of unknown state discrimination, and I'll explain, the link with the task we're considering today. I'll say a brief word about optimality of the scheme that I introduced. This part is really quite the simple part. And then I'll talk briefly about how you can actually view this in a linear optic context. And you'll see like nice equivalence links between the statistics that you can get from quantum circuits and the one that you get from interferometry, basically with single photons. So with that, you may wonder what is the swap test. So I guess most of you must have heard of it. It is basically a discrimination test that if you have two unknown quantum states in the input, you basically control swap them using an ancilla. So if the ancilla is 0, you will act as identity, and if it is 1, you'll swap the two states. And then you measure the ancilla, and you can see that the probability actually depends on the overlap of the states. And so really, all this part of the circuit here doesn't depend on the input state. So this is why we talk about unknown state discrimination. It's not a circuit which is tailored to these particular states phi and psi. And so how can you use it for state discrimination? Basically, if you get the result 0, you say that the states were the same, and it's probabilistic. So for example, if you start with orthogonal states, you'll see that you have half of a chance of being wrong about them being equal, right? And if you get the result 1, you'll say that the states were different. And basically, you can work that out and see that you can never be wrong about the states being different. You'll never obtain the outcome 1 because when the states are equal, this probability here is actually 1. So you'll always obtain the result 0. And so we say that this test, it satisfies the one-sided error requirement because it can only be wrong, in one way. Okay, and so you could think of a simple generalization of that, where you want to bring to lower this probability of being wrong, which is here. And the way you can think about it is if you have many copies of these two states, you could just repeat parallel swap test, right? And you'd get an exponential improvement in this probability of failure, exponential in the number of tests that you do in parallel. But we're more interested, as you saw in the previous slides, in some asymmetric setting where you have actually just a single copy of the state phi and many copies of the state psi. So this is the kind of generalization that you can think of, which is kind of straightforward. So here I represented it for 4 input states here. So you have a single copy of the state phi, various copies of the state psi, and you first perform a swap test on the first 2 input states here, and then you use the bipartite output states, and you do a kind of parallel swap test between this guy and this guy, and this guy and this guy. And basically, what you get in the end is the following probability for obtaining 0 for both ancillas. So here you see we measure these ancilla on the computational basis. And so again, this device satisfies this test. Basically, if you use that for state discrimination, it will satisfy the one-sided error requirement, because you see the probability of obtaining this outcome is 1 when the states are equal. Right, and in the orthogonal case, let's say when the 2 input states are orthogonal, you'll get a probability which is better than before. And so you can actually generalize that in a really straightforward way by induction. You just add more copies of the state psi here, and you do more parallel swap tests again and again. And in this generalized version, you get the following probability for obtaining 0 for all the ancillas. So, I mean, the generalization is really straightforward. It works when this guy here is a power of 2, because basically you see that I double the number of tested states somehow at each step. Okay, but more importantly, you also see that when m goes to infinity here, this really retrieves the statistic that you'd expect from a projective measurement, right? Because you can basically map all this outcome, like all zeros to the outcome 0, and all the other outcomes to the outcome 1, and you'll actually retrieve a projective measurement, basically. So this circuit approximates a projective measurement, and in a universal way, as I described it before, where actually you see that the whole circuit here, it doesn't depend on the input states. So I could perfectly take this guy out, consider these as my program states, and all the rest as my big circuit, and then post-process the outcomes and just output this binary 0, 1. Okay, so this is nice. We can have results about optimality of this scheme. So we actually derived a bit more general result for these task of unknown state discrimination. So again, unknown state discrimination is the task of saying if states are equal or not, and you have really no prior information about the state. So what you can actually show is if you take any identity test, so here you're considering the task where you're given m different states, and you're asked the question whether if they're all equal, if they're all equal, or if at least 2 of them are different. And under if you take a test that satisfies this one-sided error requirement that I mentioned before, you can actually show that the error probability of this test will be at least this value. So maybe just to give you an intuition of how you derive this kind of result. Because you're dealing with unknown quantum states, you can actually show quite easily that the only thing that you can do with those is try to project them onto the symmetric Hilbert space, because in the case where they're all equal, you'll get this product of psi states. And if you apply this theorem to our case, where we restrict the input to be a single copy of a state phi and many copies of a state psi, so in this case, that would be mapping this guy to phi and all the rest to psi, you actually show that this generalized swap test that I showed you before has optimal error probability in this case. Okay, so you may be wondering what's the link with universal projective measurement here. So the reason is quite intuitive, in fact, because if you want to discriminate between, let's say I have this state phi, and I'm asked whether it's equal to another state psi, which I perfectly know, and phi is totally unknown, and psi is perfectly known. Well, I can build, in principle, a machine that will implement the projective measurement onto psi, and that would be the optimal way of saying if phi is equal or not to psi. But here we're in a case where we don't know information about phi nor psi, but we have many copies of psi. So basically what we do is we extract information of the many copies of psi, and using somehow this information, we implement the closest optimal strategy for discrimination. And since in the limit it is a projective measurement, this is why we can also get this optimality result for a projective measurement. So basically, this theorem here, so under the one-sided requirement, any two outcome measurements that use some copies of resource state has at least some distance with a universal projective measurement. It basically tells you that it gives you a limitation on what you can do to approximate a projective measurement that works for all inputs. And this is really saying that if psi is an unknown state, there is limit on the quantity of information that you can extract about psi if you have a limited number of copies of it. And so in this case, if you look at the generalized test that we had before, it actually, this bound is tight, is equal here for this test, test, and you can deduce that this, in this really particular sense, that this guy is optimal for this approximation of a projective measurement. Okay. So up to here, it's really really straightforward generalization of the swap test, and we may be interested in how are we actually going to implement such a thing, because in theory you can just multiply all these controlled swap gates, but experimentally they would be kind of hard to implement. So this is what motivated us to look at linear optics. So yeah, here just a brief introduction. Basically, if you're not familiar with linear optics, all you need to know about linear optics for this talk. So if I have two perfectly distinguishable photons that mix on a beam splitter, so this red dashed line here is a beam splitter. If I mix those two on the beam splitter and I measure the number of photons with these guys, you'll see that I have three possible configurations if I really don't care about other degrees and freedom than just the number of photons. And so, for example, this is the event that you detect like 2 photons here and 0 there. Here 1 each in one branch, and here 0 and 2 photons there. And because the photons are perfectly distinguishable, you can just say that they evolve basically independently, and so it's kind of a classical evolution where this guy will have half of a chance of going here and half of a chance of going here, and the same for this one. And so if you combine everything, it gives you this, right? And now we have this kind of a fundamental effect, which is called the Angou-Mandel effect, where if now the two photons are perfectly undistinguishable, you'll get behavior which is really different from the previous one, where actually, so this is called bunching, actually the two photons will always go to the same branch. So you see either up or down with half priority each. Okay, and you can generalize that in a really simple way, where you consider two photons that could be partially distinguishable, and you compute the probability of bunching, and you obtain the following equation. And so here probably you start seeing the link with the swap test, because this is exactly the probability that we had before of obtaining the outcome 0. And so here I can really use this this guy to implement the same kind of test that I had before, the swap test, just by saying if I get bunching, I'll say that the states are the same. If I get anti-bunching, I'll say that the states were different. And so in this sense, well, you can say that the swap test and the Angot-Mandel effect are equivalent. This is a bit more refined statement in this article. And so in which sense are they equivalent? It's more like in some weird sense where you can say, I can post-process the statistics that I get from one of them to obtain the statistics that I get from the other. And so this is really a statement that we're going to generalize, because remember we had this simple swap test, and we derived the generalization in the circuit picture. And so we also want to generalize this statement over there. So this is what it looks like. It's a bit messy. So these states in the input, they are single photon states. These are just shorthand notations for single photon states encoding some quantum states in their additional degrees of freedom. So for example, I don't know, these could be states of polarization or time-bin encoding, whatever. And they're going through some big interferometer here. And in the output, we measure the number of photons of each mode. And there's some efficient post-processing, which will output either 0 or 1. So you see that basically this D here, it is the vector of the number of photons that you measure in each output mode. And this function pi is kind of a test function. So before it was, in the previous example, it was kind of simple. It was just if you get 2, 0, 0, 2, I'll map it to 0. And if I get 1, 1, I'll map it to 1. So this is a bit the generalization of that. And this interferometer, it is described by the unitary matrix over here. So again, if you're not familiar with linear optics, you can basically describe any passive linear evolution by a unitary matrix, which will tell you how the creation operators evolve, through this through this evolution, basically. So okay, and so the main statement is that we're able to find this test function such that we retrieve the statistics, the like binary statistics that we had in the generalized swap test. Right, and so you may wonder what is this test function. So it's basically quite simple. It's just a sum of plus ones and minus ones. So if you want some like mathematical intuition of what this is, it is basically the reverse transform of what the unitary matrix is doing to the quantum state. Maybe I won't enter too much into the details, but maybe more importantly, you can see that this function, it only depends on the parity of the number of photons, right? Because this is just minus 1 to the power something. And for that reason, you could think of an experimental setup where you actually decide to measure not the number of photons directly, but the parity. So I was told that there are experiments that directly measure the parity instead of the number of photons. So I guess that that could be a possibility for relaxing experimental requirements. And right, and so with that, we get an equivalence between this Hadamard interferometer. So yeah, this is called Hadamard because basically it is related in other fields to what is called Hadamard-Walsh transform. Right, and it's just because the unitary matrix that I showed you before is some tensor product of Hadamard matrices. And here again, the equivalence, it's kind of hard to claim. It's not really an equivalence. Is that you have a way of post-processing the statistic of one of them in some non-trivial to give some non-trivial outcome, which maps to another post-processing of the other. So really, the important point here is that you cannot just take a quantum circuit and map it to an interferometer. Like it is believed that they have bosonic computation, and the is maybe not universal if you don't do adaptive computing. So it's not like you can just take a circuit and map it to linear optics. And it is actually quite surprising that you can retrieve these optimal tasks using only linear optics. Right, and maybe I'll say, so yeah, a brief word about the complexity of this interferometer. So here I represented it for 4 input modes. So you see it's kind of really basic, like 4 beam splitters and a few detectors in the output. Maybe a quick precision that I can say is that you actually don't need 4 detectors, but only 3 of them, because this thing conserves the number of photons. Basically, you could deduce in a perfect setting, you could deduce the number of photons in the last mode just by having the total number of photons in the input and the number of photons in each of, for example, these 3 guys here. Okay, and when you generalize this statement to any size, it's really it can always be built from balanced beam splitter. Right. So just how long do I got? Okay. So cool. So I'll just say a brief word about how you can actually prove such a statement. How you find this post-processing function, let's say. So basically, I told you that the way you compute these probabilities here is by using this unitary matrix and its action on the creation operators. And so maybe some of you are aware of boson sampling. So this is kind of the same kind of calculations that we do. You get output probabilities that depend on a mathematical function, which is called a permanent. And so you need a way to assemble those different permanents through this, through this function, right? So that you actually get a simple expression. So for those of you who don't know, like the permanent is something which is in general quite complicated to compute. And here, the reason for which there is some kind of efficient way of doing things is because this matrix here is highly structured. And so the proof is actually quite nice. It's using the group structure within the lines of this matrix, and it's a statement that you can actually generalize. Because I mentioned that all this was for number of inputs, which is a power of 2, but you have actually quite a nice construction which works in the general case. Right, and so I'll summarize the results. So I presented to you this simple generalization of the swap test. I showed it was optimal not only for this kind of weird state discrimination task, but also for approximating a universal projective measurement. And I gave a linear optical implementation with a Hadamard interferometer. And so, possible future work could be looking at coherent state encoding, because I guess producing these single photon states is quite technical in the lab, and so of course going to coherent states would give a restriction, but probably I mean, we're investigating this, but probably you'll get the same kind of results with less experimental resources, also proof of concept experiments, and maybe more on the theoretical side, actually looking at sorry, what was I going to say? Yeah, I forgot what I want to say, but I thank you for your attention, and you can find all the results in this reference here.
Thank you, that was a great talk. Do we have any questions?
Some of them possibly. Great, thank you. You made a universal simulator of projective measurements of rank 1. Do you have anything for larger rank projectors?
No. For now, I mean, it's the only thing that we've been investigating. Actually, it was more like kind of a fun result that we stumbled upon. So I mean, this is why I guess there's really a lot of ways that you can think of generalizing. For example, it could generalize to these simulable measurements in a quite straightforward way, I think. And so we didn't investigate those, but that could be a possible extension, yeah.
Okay, about the equivalence of swap tests and the interferometers, one great thing of the swap tests is that you measure the ancilla and you still have the states that you have tested. So in a sense, it's not a completely equivalent. The probabilities are the same, but
right. So this was, I mean, already discussed in the reference that I showed you. You know, which claims this equivalence. Actually, in here they answer this this concern that you have by giving actually a circuit picture where you don't need any ancilla, which basically amounts to doing kind of a Bell basis measurement on your input states. So yeah.
And finally, I have the impression that the proof of principle measurement is already done in Rome group of Fábio Chiarrino when they are in another experiment involving Ernesto Galvão, Daniel Brody, when their concern is about identity of photons. That in a sense it's
Interesting. Okay.
your measurements. Okay.
Do we have any other questions?
Hi, thanks for a great talk. You mentioned that kind of there is some relationship between the work you've been doing and boson sampling, which made me think that, so all the stuff that you've talked about was kind of in the perfect noiseless regime. Have you thought at all about effects of noise or photon loss or things like that?
That's a really good point. I mean, already you see that I would say a first flow here is really in terms of optimality, because all these results, they're proved under this one-sided error requirement. So, you know, you assume that you can have all your errors coming from the same source somehow by saying in the state discrimination picture, by saying that the states should be equal while they're not, for example. And you'll see that in the experiment, you'll never have this kind of one-sided requirement. So I guess the proofs would have to be rewritten for this particular thing. So about the noise, we actually derived the results in the coherent states encoding, but it was to actually prove that if you generalize in this way. So for example, in experiments of quantum fingerprinting, you mix two train of coherent pulses on a beam splitter, and so basically you can generalize. So it is quite the same as doing a swap test that I showed you before, and you can generalize this in a simple way using this interferometer. And we actually derived here kind of a noise model where indeed you don't get this one-sided error requirement, but you get an advantage of in the error probability, of course, when you look at the larger interferometer. So yeah.
Thanks.
Okay, then let's thank Ulysse again.